Great, we can get started. So welcome back, everyone. Welcome to our first tutorial for this year, which will be on Xarray, which is a very useful package for handling multidimensional data sets. Before I introduce our speaker, I just wanted to remind everyone that this is a tutorial session, so please ask your questions in the tutorial Slack channel. So that's OHW22_tutorials. And ask your questions there throughout. I will be interrupting Deepak as needed with questions as we go. So feel free to ask questions as we go, especially if it pertains to something at that time. And then we'll have some time for questions at the end, probably as well. If you like questions that someone else has asked in the Slack channel, please use the +1 emoji, and then that will help us know what are the most common questions and make sure that those get answered. All right, so we are very lucky to have Deepak Cherian here today, who will be presenting on Xarray. Deepak is a physical oceanographer at the National Center for Atmospheric Research in Boulder, Colorado. And he's also a maintainer of the Xarray package. So we are very lucky to have him speaking. Deepak, go for it.
Great. Thanks, Paige, and thanks to all the organizers for the invite. I had a lot of fun doing this 2 years ago, so I was very excited to do it again. One second, let me close my window. So yeah, today I'm going to talk about this package called Xarray. And importantly, Xarray is a Python package. And as of this moment, I'm not aware of any package that's similar in any other language that is as popular and widely used, which is unfortunate because, as you will see, it is very cool. So yeah, my usual way of trying to show this is if you start to try and define what Xarray does, it gets kind of complicated and abstract. So really, we're just going to jump into it, read a data set, and then talk through the whole thing. And so the goals for this lesson are really that you understand that Xarray provides some basic data structures. These data structures are very useful in the type of analysis that we like to do with our data sets. There are two structures. One's called a data array, one's called a data set. You can read and write various file formats with Xarray. And there's also many packages that build on top of Xarray that are super useful for things that you would usually want to do. And so we'll just start. I'm assuming all of you can follow along and you're all on a binder hub and all of these cells should work. So go ahead, run the first one and then run this other one. And so what this is doing is we've imported Xarray as XR. That's kind of a little conventional naming. And we're going to start, like I said, by loading an example data set. Xarray is nice because if you call XR tutorial load data set, there are a bunch of data sets that are basically sitting on GitHub and you can pull really easily. There are a bunch of others. Today we'll look at this air temperature one because it's quite simple. This is air temperature over North America. It's from NCEP. And so when you do ds equals this load data set command, you get a ds thing and Xarray objects have very nice representations. If you just have ds like that at the end of the cell, it will show you a HTML representation of that data set. And so let's talk about it, right? So the first thing you see here in this representation is dimensions. And you see there are three of them, time, lat, and lon, right? So it's a three-dimensional, there are three dimensions in the data set. Let's skip coordinates for now. Let's go down to data variables, and those things are clickable. So the first one is just something called air. It's got 3 time, lat, lon. So that's telling you that it's a three-dimensional array. If you click this little databasey thing, you'll see a bunch of values down there, which is 240, 242, and all that. Click to the next one. So that tells you attributes. It tells you that this is 4 times daily air temperature at a pressure level of 995. The units are in degrees Kelvin, so that makes sense why you're saying 242. And there's a bunch of other stuff in there. And so at high level, this is what Xarray is, right? So you're used to somehow reading in your data as a bunch of numbers. But you don't just analyze numbers. There's a bunch of metadata that's associated with your data. Things like the last dimension, in this case, for example, is lon or longitude. The second one from the last is latitude, and the first one's time. And if you're coming from like a a MATLAB background, for example, which is what I was doing before I discovered Xarray, you're used to carrying this around in your head, but the first dimension of my array is time. And then,
Deepak, sorry
sorry.
for the interruption. Could you zoom in a little bit? It's a little small on our screens.
Sure. Is that better?
Yes, that's better. Thank you.
Great. Sorry about that. So yeah. So we're used to just reading numbers from a data set, and then you keep a lot of metadata found in your head. These would include things like what the names of those dimensions are, the fact that the last axis of your array is longitude in this case, or maybe it's time for another data set, the fact that you're—
Hi, Deepak. Sorry, my bad. I've gotten a request to have it be even larger, if you don't mind zooming in even more.
Ooh.
That is great.
All right.
Thank you. Sorry.
Yeah, no worries. So what Xarray does is it takes all that metadata that you usually keep in your head and put it in the structure along with the actual data that you're working with. So in this case, temperature. And if you look at this representation, you can see that it's got 3 dimensions. You know what those orders of those dimensions are. And the extra cool thing is when you look under this coordinates a little bit, you'll see there are 3 coordinates, each corresponding to a dimension name, so lat, lon, and time, and they're bolded. And there are a bunch of values associated with them. So if you clicked on time, you'll see it starts January 1 at midnight. The next time step is 6 hours later, and so on till the end of 2014. If you click on a longitude, for example, you see it goes from 200 to 330. And if you clicked on latitude, you'll see it goes from 75 to 50. And so it's actually backwards, which is interesting. And again, you can click on this little icon and you get a bunch of attributes. In this case, it's telling you that lat is actually the latitude. It's in units of degrees, which is great. Similarly for lon, similarly for time. And so as you can see, this is a data set. It's got one array, which is like a 3-dimensional array at the bottom, but then it's got a whole bunch of this metadata that's all of this together. If you come from MATLAB like I did, people tend to create structures, very complicated structures that have all of this information, but there's no kind of standardized way of doing it. This is what Xarray gives you. It's like a very standardized way of taking your metadata, combining it with the data, and then, as we'll see, helping you use that metadata to write your analysis, which ends up being very, very useful. There's some details here, but basically tutorial open dataset has actually in the background downloaded a file and done a bunch of stuff to get that in, but we'll just kind of move on and you can kind of dig into this later. And so, like you said, we spent a bunch of time looking at this data set representation. So what's in a data set? The answer is many data arrays. So that's kind of the lower level structure that's just wrapping a single array. And in a particular data set, you can have multiple arrays. So technically in this data set, there's air, there's latitude, longitude, and time. So that's 4 different arrays that have been wrapped up together because it makes sense to keep them together. And how you extract data, so you can use it like this. And so the concept here, I don't know how much Python background you guys have at this moment, but you can think of data sets and data arrays as dictionary-like containers, which means if you're familiar with Python dictionaries, a lot of those concepts carry over. So if you had a dictionary, you could use the square bracket with a string or some other kind of label to pull out the value associated with that key, which is air in this case. So you can do the same thing with that data set, and you can see it comes out with a data array whose name is air, and again, it's 3 dimensions. It's got a bunch of values, and you see that latitude, longitude, and time have come along with that data array from that data set. And the reason is because those values are associated with these dimensions, and so it's going to be useful for our analysis if we know what actually those coordinate locations are. And not just that, oh, the last axis is sized 53, which is kind of useless. But if you know that the actual values of those longitudes, then you can start to do something useful with it. So that's, this syntax will always work, basically. And then in some cases, you can actually do ds dot as just a shortcut. Sometimes where this won't work is if you have a variable that's named mean, it's going to be problematic because data sets have other methods on them, as you'll see soon. Any questions at that point? At this point, we've kind of quickly looked at data sets and seen data sets as a collection of many data arrays, where each data array is wrapping a single array. I'm going to go forward. And so what's in a data array? And again, we've already kind of seen all of this, but we'll just look at it again. The most important thing is the fact that dimensions have names. So in MATLAB or something, for example, you would usually be saying, hey, take the mean along axis 1 or axis 0. If you were just used to NumPy, axis equals 0 or 1 is like a common thing that you would keep typing. The key point of Xarray, again, as I said, is that there's a lot of metadata that goes along with your data. And that ends up moving through your analysis pipeline if you use Xarray. The most important piece that I found, or the most useful bit, is usually the fact that dimensions have names, right? And so if you do gs.arr, which is a data array, .dims, you get 3 dimension names, and these are in the order of the axes. The second piece of data that we've already seen is this .coords, which is coordinate labels or points. I like to think of those as if you made a figure, these are the points on the X or Y axis at which you would draw dots or something. So like axis tick labels could be a way to think of these labels. So it tells you the points of the grid points, grid locations at which you have data in coords. You can extract all of this information out as its own data array. So like I said, here I pulled out lawn, you can see it goes from 200 to 330. And you can see all of these attributes have come along with it. The standard name of longitude, it's got units of degrees east, etc. And this is just another way of extracting all this information out of that one big data set. And the last piece of metadata, which we've also just looked at, is the fact that there are attributes or attrs, ATTRS, which is just short for attributes. And we've already looked at this again. But what's key to note is that, again, this Python dictionary has come back. And in this case, the keys of this dictionary are always strings, the long name, units, position, etc. And the things on the right are also strings, I guess, well, mostly strings. So sometimes you can see there's an integer and down here there's an array. But really, this is just a Python dictionary, so you can add your own random attributes. So here, for example, I added who is awesome. And I said the value should be Xarray. And so if you go to ds.add.attrs, you'll see it's there at the end. And really, you can add anything you want. The limitations really just come in when you try to write to disk, and that file format maybe does not like what you have. And so just to show that off again, if you go down to attributes here, you'll see that here's the new attribute I added with the value that I added. So you can put in your own things, and it works pretty well. And so at this point, we've looked a lot at the metadata that goes along with Xarray. So things like dimension names, the fact that there are coordinate locations at which you know the values that are in your array, and that there are arbitrary attributes here that you can add and remove as you wish. But one little thing is that, you know, at the bottom of this, there's just a bunch of numbers. And in this case, it's what's called a Numpy array, which is basically a bare array, n-dimensional array structure that just has numbers. And so you can extract that out too by saying .data. We'll come back to this concept later in the week when you talk about Dask. But at the moment, this notebook basically focuses on NumPy arrays, which are just these bare arrays of just numbers, right? And so that's what's sitting at the base of all of this. There's a NumPy array, and then there's a bunch of metadata on top of it, and Xarray lets you handle the two of those together in very consistent fashion. And this is very helpful because we like to think in terms of the metadata, as I will demonstrate next, as opposed to things like axis equals 0, which is kind of hard. This is also, you know, it's just telling you that the data that's sitting under there is a NumPy ND array. Okay, and so the review for this little section is that Xarray provides 2 main data structures. One is a data array. This wraps an underlying data container, in this case, a NumPy array, and it adds a bunch of associated metadata. And then we have data sets, and data sets are dictionary-like containers of data arrays. And so just to be clear, what that means is there's DS. This air is a name, air, that maps to a data array that is wrapping this little NumPy thing. So it's like layers on top of layers on top of layers, but it's nice because that's usually how our data sets are organized. Like in a single netcdf file, you might find multiple data variables, multiple coordinate variables. And this Xarray structure is a way to represent all of that in your Python session. Okay, I think I'll pause there. If people have questions, feel free to ask them.
I don't see any questions in the Slack yet.
Okay. And so, this first little big chunk of the tutorial is focused on the fact that Xarray lets you carry a lot of information. But here's why that's pretty cool, right? So here's a little small bit of analysis, right? So what I'm doing is I'm taking out the latitude, I'm taking out the longitude, I took out the air temperature, and I used .data to pull the actual values. And just to illustrate that, so run that and just look at what lon is, and you can see it's just a bunch of values, right? The fact that these are longitude values is encoded in the name of this variable, which is, I think, a common pattern everyone's kind of used to. And then this is a little bit of matplotlib, but I just make a nice little figure, right? So you can kind of see North America. This is air temperature, so you can kind of tell land from ocean. And so, yeah, this is just matplotlib stuff. I told it to put lon on the x-axis. I told it to put lat on the y-axis. And I told it to pick the first time step. And the only way I did that was to specify this index 0 along the axis 0. So I've implicitly in my head, I've mapped, I know the fact that the time axis is the first axis. So I've used that here, right? So this is an example of this idea of you carry a lot of metadata in your head usually. And what Xarray lets you do is not do that. Which we'll see in the next little bit. Another common thing that you might do is take the mean along axis equals 1. If you come back to this code a year later, it's very unlikely that you know what this means because you don't know, that point, you've probably forgotten what the order of axes were. In this case, I think it's latitude, maybe. You would have to go back and then compare the size of the latitude array versus the size along the second axis, ... so on and so forth. So that's how I'd used to do things. And then I discovered Xarray. And so here's how you would do the same thing with Xarray. And here's what I did. We had that data set. I then pulled out the air temperature variable. I said, hey, give me the, this should be 0, sorry, typo. But this gives me the 0th index along the time dimension. It doesn't matter where that dimension is. I just told it, and it knows enough about the data to tell it to do that for you. So I just told it, I want to see the first time step. So I said time equals 0, and I give it to this nice little helper method called isel. And then I said, plot that. And I said, put longitude on the x-axis. Right. So just to illustrate that again, I did ds air, and I called this isel time equals 0. And so when you do that, you'll see you've got a 2D array that comes back because you've just picked one time instance, and that's a data array. And you can do this nice little plot. And it's super nice because now you see that all that metadata that was in that object is now suddenly on the figure. So if you look at the color bar, you see it has got a nice little label. It tells you that this was daily air temperature at sigma level 995, along with the units of degrees Kelvin. The x-axis is labeled longitude. And with the units degrees east, the y-axis is latitude with units degrees north. And everything looks kind of nice. The last thing I did in the previous section was I calculated the mean. So here, for example, I'm going to say, I want the time mean of this data. And so there you go. You tell it to take the mean, dot mean, and you give it time. So where in Numpy, you would usually say axis equals 0, 1, or 2. In Xarray, you give it the dimension name. And you can be a little more explicit where you can say dim equals time. And that's, it's a little more readable. I say, now I took the air temperature, I took the mean along dimension time. And again, this is a 2D array, so we can do a nice little plot. Let's see.
We have a question in the Slack for you.
Yeah.
What is the difference, if there is one, between .data and .values?
Good question. So in this little data set, there is no difference. So .data gives you the underlying array. In this case, it was Numpy array. If you do .values, in this case, it's also a Numpy array, but this is basically always a Numpy array. This won't make really much sense at the moment. We'll see this on Thursday with Dask, but you can, Numpy is just a single kind of array type. There are a bunch of other array types. I think I actually have a demo a little later on. And so data will give you the underlying array type without any changes. Values will try to convert that underlying data type to a Numpy array. It's a little subtle, but that's what it is. Usually I'd recommend you should be using .data unless you really know what you're doing.
Great, thanks.
Okay. All right, so at this point, I hope I've convinced you that the fact that you can carry metadata around with your data is super useful and lets you write very readable code. That your future self will thank you. I've usually found this. When I come back to a notebook, it's usually somewhat clear what I was doing, just because of the fact that all of the code looks so readable. Like I took the mean along the time dimension and then I made a figure. Great. All right, so we kind of already saw this in the previous one, but this is kind of just getting more into it. So commonly, you have this big three-dimensional array, but you want to look at subsets. And so this little section looks at extracting data or indexing. And so we'll see another example of the power of carrying around metadata. In this case, specifically, we'll look at the power of coordinate labels. And so let's go back and look at our DS. And so this little section focuses a bit on this stuff that's up here. And so, like I said, the way to think of these little coordinate arrays is to think of them as grid point locations, or tick labels along an axis is another way. But these are basically the points at which you know the values that are in this little air temperature array. But because we have a bunch of these values, we can use them for very conveniently extracting data. And if any of you in the audience has experience with pandas, a lot of the stuff actually is copied from pandas. And actually under the hood, we actually use pandas data structures to make all the magic happen. So we're used to using a pandas index to do nice kinds of things. A lot of those concepts carry over to Xarray. But if you haven't used pandas, don't worry. I'll demonstrate some of that right now. Okay, and so this is a 3D data array. And one dimension is time. And in particular, time selection is super convenient. So here, for example, we use cell, which selects along with labels. And this is different from another one that's called iCell, which uses indexes or positions, which is the thing you're probably used to coming from NumPy or MATLAB kind of backgrounds. But first, we're going to look at the power of label-based indexing, which is the idea that you can use this metadata that's in here along these coordinates to help you extract data. So the first demo is this one. I said 2013-05 in a string, and I said select that along the time dimension. And what it does is it's going to give you all the values for May 2013. So it starts May 1st at midnight and will end May 31st at 6. So for a 6-hourly data set, that would be the last time step that's in May. So that was super convenient, right? Usually I would do some kind of like shooting algorithm, right? You would look at the values of time and then do something like, oh, what's the 50th index? Oh, that's a little too early. Let me multiply by 100. Something silly like this. You'll keep shooting to try and find the right location. Oh, now I'm in May, so I'll move back a bit and then I move forward a bit. It's all kind of silly once you get used to this. So yeah. If you just wanted the whole month of May, that's how you do it. You can, there are a few more convenient things. So you can say slice is to say pick everything that goes between the first value and the second value. So in this case, it's going to go between the 1st of May to the 31st of July. So you can see that here, it started on the 1st of May and it stopped on the 31st of July, right? The other thing I'll show you is also you could do cell, say, I just wanted the whole year of 2013. There. So it starts in January 1, ends in 31st of December. And so, there's some magic that's happening in the background. Xarray takes this little string, it tries to figure out what you mean. It looks at the type of that time variable. It's like, oh, these are date time, so I can do some high level thinking and kind of try and guess what the user wants. So it's super convenient when you're doing things like time series in particular. Now, the thing is, you may want values at a particular value of longitude, for example. So here I'm saying 240.2, and I'm saying find me the nearest value, which I've usually found is pretty useful, right? Because sometimes there's a little small bit of floating point differences, but in many cases, I just want the nearest value. So I did that. I said 240.2. Here's what came out. It's a 2D array. Makes sense. I've taken out one dimension by just picking one point along longitude. That value has still carried over. You can see that it's used the value 240. That was the one that it thought was closest to 240.2. And then it gave you a 2D array of temperatures at that point. A common problem that you may have is like trying to subsample a gridded field along a trajectory or something like that. Actually, sorry, in this case, you want like a little small subset square. So here's that. So I've told it to find the nearest point, and it takes, along 240.125, 234 longitude, and then 40.3 and 50.3 latitude. You see, you get out a 2x2 matrix. So you got there are 2 along long and 2 along lat, and it gets you the 2x2 matrix that comes along with that for all time. So you end up with a 3D output. So yeah, there's a lot more that you can do. I encourage you to look at the Xarray documentation. This notebook mostly demonstrates things that hopefully will be useful for the projects that you'll end up doing, but it's usually capable of a lot more. And I would encourage you just keep looking at the documentation as you try things.
Deepak,
Okay.
we have another question.
Mm-hmm.
Are there any handy tools for converting .mat data files to something that can be opened with Xarray?
No. So usually I do this. Load map will help you load. So basically, there's no easy tool, and the reason is because netcdf files and Xarray structures have a lot of metadata, and there's no standard way of expressing that metadata in MATLAB files. And so usually what you'll have to do is create a data array, read the data in, then create your own data array or data set, add all the attributes and stuff, and then write it out to a nice netcdf file.
Okay, there's another question. Conversely, is there a tool for generating .mat files from Xarray datasets?
Oh, I think there's a safe mat. There is a safe mat. So that's one. But again, you would have to do this. You'd have to think about it because again, MATLAB files don't have all that metadata. So you have to take this very rich data structure, pull out all the arrays, put them into a nice form, and then write it. So it's kind of a pain. But MATLAB is kind of a pain generally, I think so.
Okay, thanks. There are a couple more questions that have come in as well. Is the endpoint of an Xarray slice inclusive, unlike a standard Python slice in which the endpoint is exclusive?
Yeah, so this is a very subtle and good point to bring up. It is inclusive. And it's inclusive when you're doing cell or when you're using these coordinate labels. So by inclusive, we mean is 2013-07 really means all of the values in 2013 July, which is where you see here. This is one of those things that we've inherited from pandas. So if you come with a pandas background, this will be familiar. But that's a good point to bring up. When you call .cell and you're using these coordinate labels to do your selection, it is inclusive, and the next one you'll see, which is positional, is exclusive or open on the right-hand side of the internal.
Okay, thanks. Another question. When you do a .cell, so ds.cell time equals 2013-05, like you were just showing, is the 2013-05 converted to date time 64?
Yeah, I think that's a good way to think about it. I don't actually know all the magic that happens under there. But yeah, I think that's usually the way I think of it.
Okay. That's all of the questions for now.
Okay.
Thank you.
Yeah. So right. So what we've seen now is that when you extract data, it's usually nice to use .cell because there's a bunch of this metadata that you see over here up into this coordinate section, and you can use that to your advantage. So you don't ever, nobody ever thinks, okay, I should pick out the 10th index of my array along axis 2. You usually want something like I want 240 degree east or something like that. And Xarray allows you to stay at that higher level because you have all this metadata that you've associated with your data. But sometimes it is actually useful if you wanted to pick out the 2nd or the 3rd or the 10th index from an array. And so you can do that too. So now we call this ICEL, which I've always thought of as select using an index value or an integer that tells you the position, which is why this is called position-based indexing. And again, usually in NumPy, you would do something like this, for example, and that's a 0 along axis 0, 2 along axis 1, and then the 3rd element along axis 3 in Xarray, because these axes have names as dimension names. You could say something like ICEL time equals 0, lat equals 2, or lon equals 3 to match what I put up there. And when you do that, you get a single value, right? Because you had a 3D array and you picked one single point in there. And so you get out a single value, but you've still carried the metadata. So it still tells you that, hey, this was the value at 70, 207.5, and 2013 Jan. And those end up being the coordinate locations associated with location 0, 2, and 3 along those axes. And this comes back to that point. We can demonstrate slicing. So you just do slice 10. This will give you the first 10 points. So the indexes go 0 to 9. And I think if you try it, you'll find that this little, with ICEL, it follows kind of Python style semantics. Right. And so you'll see I asked it for the first 10. So it'll give you an output where the latitude dimension has size 10. And it's gone from 75 to 52.5. So it's, preserve that order because you've gone in, just asked it for this first 10 values. So yeah, and then, so, you can always go back to this style of indexing. This is sometimes useful if you're like converting a script that used to work with a Numpy array to now adapt it to work with an Xarray thing. This kind of stuff can be useful. Okay. All right, so that little section was on pulling subsets of data out of your data set. And so the next little bit, we'll go try and look at simple computations and look at little concepts that apply when we start to do that. Yeah, are there any questions at this point? Or if not, we'll move on to the next bit.
You can keep going.
Sweet. All right. So now that you've read all this data and I've showed you that, okay, you can use all the metadata to nicely extract your points, this little bit shows you why all that metadata is helpful when you're trying to calculate things. That's pretty cool. So here, what we'll do is we'll think of the same data set, and we know that it's got values at a bunch of points. And sometimes you want to figure out what the area is per grid cell. And the reason you might want to do that is you want to calculate the mean temperature per unit surface area. Sometimes you want to calculate the mean, but weight by the area of a grid cell or something like that. But here, it's really just an example of a computation you might try, and it's nice because it illustrates a few concepts. And so here's the thing we want to calculate. This says the area on a sphere is something like the square of the Earth's radius, the spacing in latitude, the spacing in longitude, and cos phi is latitude. And so we start, so we set R is the Earth's average radius, d phi and d lambda are, in this case, I convert from degrees to radians. So all this is fine. This is kind of standard. The magic that happens is down in this little bit. So we're just going to run it, and then we'll look at each of these with new variables we've created, that it's dlat and dlon. So we look at dlat. This is the delta spacing in latitude as a function of longitude. This turns out to be a constant on the Earth. And so you see that the way we've created it is to say R, which is a constant, D5, which is a constant, which is nice. And then I've used this thing that is called XR_ones_like. So we'll jump in and look at that a little bit. And so what it does is, as it says, it creates a bunch of ones, but it puts it in a data array that looks like ds.add.lon, which means that it comes out as a 1D array with all of this metadata. So this is one kind of useful concept. Is usually it is kind of useful to use things like ones_like or zeros_like to create a data array that looks like some other data array, but just has these ones or zeros values, right? And so because I told it to create something that looks like lon, it gave it the dimension name lon. It also added the same nice coordinate labels. Technically all of these attributes are wrong, but that's one of the downsides of carrying all the metadata is you have to make sure that it is up to date. But in this case, it made an array that looked exactly like lon, but just replaced all the data values with one, right? So that's what dlat was. And the second one, so the spacing of between two longitudes along a latitude is a function of latitude because you get smaller and smaller as you go towards the poles, right? And so here's r times d lambda, which is a constant. And then this is kind of interesting. These are numpy functions. So this is numpy.cosine and then numpy to degrees to radians of the latitude. So again, here's a look at the output. This is what dlon looks like. It's a vector. It's a function of latitude. This time it's got different values. And you see it goes from a small number to a big number. That's because our latitude vector is going from the north of domain to the south of domain. So that makes sense. And a few things have happened here. So the first thing we've done is we've called this little numpy function. And because the latitude was in degrees, we first convert that to radians. And so this is cool, right? You've called a numpy function on an Xarray data array thing, and you get back an Xarray data array thing with the right dimension names and the right coordinate locations. Again, the attributes are kind of wrong because we haven't, in this case, you might want to change the units to radians. So again, the downside of having metadata is that it's very easy for that metadata to go out of date, especially the arbitrary stuff that's sitting in attributes. So this is something that you have to keep track of manually. But for the purposes of computation, in many cases, you can do things like, so now I can even call cos to get the cosine of that latitude, and it comes out as a data array. So usually it's kind of nice if you just try it. If you have a numpy function and there are these things that are somewhat simple, that are like, one element of the input goes to one element of the output, usually things will just work. And Xarray will pass that on down, do the right calculation, and then add all the nice little attributes and give it back to you. And so that's how the dlon ends up being this little 1D vector of spacing in meters. Is that clear? Do you have any questions?
Don't see. Oh, one just popped up. Do numpy functions work if the underlying data is not a numpy array?
Yeah, it's down to that underlying array, but in most cases, yes. Everyone tries to follow the same protocols and standards, so it tends to work. So usually the answer is to try it and see, and usually you'll find that it works.
Okay, that was it so far.
Okay, and so now we've come to two key computational concepts where you'll find that the metadata is super useful. The first one is what's called broadcasting, which is expanding data. And so again, like in this tutorial, we'll just try it and then see what comes out. So I'm going to multiply dlon by dlat, right? So that's a spacing along latitude, a spacing along longitude, multiply them to get an area in meters squared. So when you do that, this is pretty cool. You get out a 2D array. And so that's kind of interesting because dlon we just saw was a 1D array and dlat was a 1D array. You multiply them, you get a 2D array out. So the underlying concept that's happened here is this idea of broadcasting. And so the result really has two dimensions because Xarray realizes that longitude and latitude, because they have different names, these are not logically the same thing. So it doesn't actually make sense to multiply them together. If you try this, usually in MATLAB or Python, they're using Numpy directly, you usually just raise an error saying you can't multiply a 25 element vector by a 53 element vector. That just doesn't work. But Xarray is working at a higher level. It knows that these dimensions are logically different just because the names are different. And so what it does is, okay, I think what you mean is that you want me to do the multiplication and get it to a 2D result. This is nicely visualized in this little image I found in this Python data science handbook. And so look at the last column. That's the one that's applicable here. So here's a 1D vector. Imagine this is along latitude. Imagine this is along longitude. And when you multiply them, because they're different, the first one gets expanded rightwards. The second one gets expanded downwards so that they have the same shape, and then it does the multiplication. So it just repeats the values. And if you go back to how you would do this with NumPy, when I was using MATLAB, I was commonly creating these very unnecessary size 1 axes. In NumPy, you would use things like numpy.new axis, or you would reshape it to add like a new axis of size 1, which would then let you do this type of multiplication or stuff. Xarray really just does this automatically for you. It realizes, hey, these are two different dimensions, so the only way I can do this is to add a bunch of dummy axes. So it does all of this under the hood for you, does the multiplication, and then gives you back now a 2D array. So this is now an array of grid cell areas in meters squared for the whole domain. Okay. Do you have any questions on broadcasting?
No, we have a bit of a theoretical question of what's the difference between an array and a NumPy array?
Yeah, so a NumPy array is a very specific implementation of the idea of an array, and it's n-dimensional. It's dense, which is that the value at every single point is stored in memory somewhere. The opposite of this would be something like a sparse array, where you already have actual values at very few points, and so there are other schemes of storing them. And then on Thursday, we'll see about Dask, which is an array that is chunked and distributed amongst many workers in parallel that lets you do parallel operations. So yeah, the idea of arrays very general, and NumPy is a very specific array. All of those values are in memory. It's dense and it has this n-dimensional shape. So as you can see here, it's very regularly shaped. Like this top row cannot be longer than the second row or shorter. Like all these rows are the same size in all dimensions. So this like a very particular subset of the general array is a NumPy array.
Okay, thanks. We have a question. Could you please go through the diagram again and explain what's going on?
Okay. Yeah, so it's good you asked that. This concept of broadcasting is super important. So we can start, actually, you can go through all of these. So here's the first row where he says you have a 3-element vector 0, 1, 2, and you're trying to add a scalar. And what you end up doing is adding 5 here to each element of this vector to get that output, 5, 6, and 7, right? So 0, 1, 2 plus 5 gets you 5, 6, 7. One way to think of this is that you take that 5, which is a scalar, and you expand it to a 3-element vector. That's the broadcasting. And now you can do element-wise addition. So 0 plus 5, 1 plus the second 5, and 2 plus the third 5 to get the output. Then you can go to the second row, where you have a 2D matrix and a 1D vector. But these shapes are compatible because there are 3 columns and 3 columns. And how you do this addition, you broadcast the second one down, and then you do element-wise addition to get this output. And this one works kind of nicely because the shapes along the last dimension are the same, so that works. So it's actually easy in NumPy. This one's a little harder because you've started with a 3-element vector and then a second 3-element vector, but I want to do it in this kind of 2D sense, right? This one's a little confusing here because they're both the same size. But if you thought of a latitude and longitude arrays, one is 53, the other one's 25. So you can't actually add them element-wise. And so the only way to do it is to shape these arrays so that this addition is possible. So in this case, what he's done is try to basically transpose it to a column, and the other one's a row. So now you can expand one along rows, to expand the other one along columns, and then do element-wise addition to get the output. This is all the kind of stuff you would have to think about if you were not using Xarray. So my recommendation is to use Xarray and not think about it. Just set the names of your dimensions properly, and then everything will happen for you, which is what happened up here. When we multiplied, we ended up getting a 2-element output without having to think of commuting dimensions or reshaping or ordering or anything like that. Was that better?
Yeah, I think that was great. Thank you.
Okay. Well, 15 minutes. So that's kind of one key concept. So now you see why this idea of metadata, in this case, dimension names, is super useful, because it lets you do all this, what people might call data wrangling, and all of this silliness of, I wanted to get this calculation, but I had to then think about how to do the calculation in these very low level steps. But if you have things like dimension names, you don't have to think about them. The second bit is about alignment. And this is where those coordinate locations or those coordinate labels or grid point locations is going to help you mostly. So in this case, I'm just going to do this division. So I'm going to take air by cell area, mostly just for illustration. And so the one thing is that it just kind of works, right? So ds.air.icell time equals 1. I chose the second time step. This is a 2D array, latitude and longitude. Cell area, remember, is also a 2D array. So I divide those two, it does element-wise division, and it looks nice. But a common problem, and so it's done this. And so one of the things that it does in the background is to make sure that these latitude and longitude values, like these values, 75, 72.5, are exactly equal. So what Xarray is doing is like, well, if you had, I don't really want to take the value at longitude of 20 and divide it, latitude of 20, and then divide that by the cell area at latitude equals 75, right? It makes sense to line those up. So Xarray will do that for you. And this is what's called alignment, which is it tries to put the data on the same grid. It has a very simplistic understanding of grid, which is that there is a value at a given point, and it will only multiply that with a value at the same point from a different array. The definition of same point is actually pretty strict. So here, what I'm going to do is I'm going to create a common case that tends to happen, and you will probably run into when you do your projects. So I'm going to take cell area, I copied it, and I'm going to add just a tiny bit, 10 minus 5 differences in the latitude. So this is, I'm calling a bad cell area. Oh, for some reason, I decided to do multiplication there. But when you do this, what you'll find is the output is junk, and the latitude shape is 0. What's happened here is, like I said, Xarray looks for equality, and it's very strict equality, which can be kind of frustrating. And so what it's done is it's decided that 75.00001 is not the same as exactly 75.0 in the previous one. And so it decides that those two values are just slightly off, and will refuse to do that multiplication or division or addition or anything, right? The way, one nice way to check this kind of thing is to look for alignment specifically. So you can ask it, this will raise an error. And what it'll tell you is that these values along the dimensional latitude are not equal. So these are not aligned, which means all of these Xarray operations will start to give you junk. So if you run into this problem, this is what's happening. It means that your latitude values are just very slightly off, or appropriate dimension. The way to fix that would be to manually assign the right latitude. So if you know that these two should be at the same place, just make sure you tell them, right? You assign directly to that and fix that up. This is a pretty important concept. So yeah, if you notice extra nans have suddenly just appeared from somewhere, or the fact that all your points have, your data set has blown up in size, and it turns out they were all nans, this is usually what's happening. So that they were not aligned very exactly. I highly recommend that you read this Xarray documentation. And there's also this little tutorial notebook we worked on recently that covers this in a little more detail. Really goes into the different types of alignment and how you do things. So if you did one follow-up after this lecture, I would recommend you go through that notebook because it deals with things that you'll probably run into. Okay, 10 minutes. Do you have any questions there?
Nope, no questions come through at this point.
Okay, we're kind of running out of time, but everything up to now are kind of the most fundamental concepts of Xarray, which is you propagate metadata with your data. You use that metadata for analysis operations like indexing or extracting data, or doing things like common arithmetic, so you end up with these concepts of broadcasting and alignment to make sure things are on the same grid. And all of that's great, right? It all works very nicely and cool. But Xarray also has a bunch of other stuff. This is all more, slightly more advanced and slightly more complicated, but it's still super useful. And so the idea is that a lot of the times we are doing fairly repetitive computations and like very similar patterns keep repeating. And Xarray tries to provide the abstract version of those patterns. And so these are things that are called group by, resample. And group by, you can think of it as just kind of binning data into groups or histogramming and stuff like that. Calculating climatologies is also a very common group by operation. Resampling is changing the frequency of your data. So you want to go from daily data to a monthly average, that you would use resample. Rolling is kind of sliding window operation. So things like a running mean of your data. So you want to do some smoothing or filtering. Rolling is the operator you want to think about. Coarsening is kind of downsampling. So this is kind of like, I want to take 10 by 10 box averages of my data or something like that. And then weighted is the final one, which lets you do like weighted means and stuff. And this little bit is really, again, it's just for demo. I encourage you to come back when you're doing your projects, come back to this notebook and see if one of these operations will help what you're trying to do. So here's one, we have a time series, right? And this is a time vector, there's 2 years of data and it's 6 hourly. Let's imagine we want to calculate something like a seasonal climatology. So I would say group by time.season. It does some magic in the background. So it says it's figured out these seasonal labels, DJF for December, January, February, and so on. And let's calculate the seasonal mean. So it's just that. So what it's done is gone through the whole thing, is try to figure out all the points that belong in December, January, or February, and it's taken the mean of them. And it's repeated that for a while. And so you can see we've lost our time dimension, but we gained the season dimension, and the season dimension has these nice values here. And one thing you'll notice is these values tend to be alphabetically sorted. So I'll just use a little self command statement to get it in right. This is the logical order, right? So December, January, February, then March, April, May, June, July, August, September, October, November. And so you get that. And one cool thing about Xarray is plotting is super easy. So here's a data array. And we can visualize this and say, I want every season in a single panel in columns. As you can see, it's done that. It's giving you nice labels for the top. It's giving you a common color bar. It's got all of that extra metadata that we really like. So that's pretty sweet. So that's group by. That's the kind of operation you should think of if you're trying to do like binning. There's a group by underscore bins or climatology calculations, histograms, that kind of thing. Think of group by. Resampling, like I said, changes the frequency of your data. So here I said resample to monthly. M is code for month. You see the output comes out with 24 because there's 2 years of data, and that's one value. Here's one January value. The next one's in February, March, April, and so on and so forth. So that's what resampling does. There's many, many options for what the frequency is. You can do 5-day, 7-day, weekly, all of this, and it works pretty well. And then finally, one reason we may want to create that cell area is we wanted like a weighted average. So here's, I took DS, I weighted it by the cell area, and I'm taking the mean along lawn and time, and then I'm plotting it. And so here's the latitude. Oops, we can actually make this even better. Yeah. So no, that's the latitude or zonal average, I guess, zonal and time average air temperature. So like I said, many of these are common operations. So Xarray provides little abstractions that let you write it out very nicely and very readably, right? So next time you come back in the future, you can see that you weighted by the cell area and took the mean long in time. And you plotted it so that the latitude was on the y-axis. So it's zonal mean. So yeah, that's mostly a demo. Definitely go back, look to the documentation. At the end of this notebook, I have links to more resources that you can look at to find out things that are useful. Visualization. Yeah, again, this is more on the demo side. So this one, I think we already saw. This is how you would visualize your seasonal cycle. This says, take each element along the dimension season and plot it as a single column. Sometimes you may have too many columns, so you could do, hey, I want to wrap it at 2, and so it does that. Super useful. I've showed you p-color plots. You can also ask it specifically for a contour plot. So here's that. That's a contour plot and has most of those common features. And you can even take, in this case, I took the mean along longitude. I forgot to weight it. But then here's the seasonal zonal average, I guess, in some sense. And the y-axis has latitude, and you see it comes with a nice legend. So again, these are all common tasks, and Xarray makes them very easy because it's got all of this metadata that it knows about, and you can use that to annotate your plots, help you write your little mean or weighted mean or group bys quite nicely. So yeah, there's a lot more on plotting. Fun fact, it was the bit of Xarray that I really liked at the beginning, and that's why I started contributing, because it just made my life so much easier. I used to make figures all the time. Now I make them in like a 1/10 of the time. So there's a user guide, there's a visualization gallery that has all kinds of complicated things that could be good to look at, and there's more tutorial material you could follow. We had some conversations about writing and reading MATLAB files. Xarray really just works well with NetCDF. It's very inspired by the NetCDF data model. And so if you have NetCDF files, everything works lovely. You can even write to a NetCDF file super easily, ds.to NetCDF. This is a fully compliant, mostly fully compliant with what are called the climate and forecast conventions. Very nice NetCDF files. If you have to hand that over to someone else, they will also generally like it very much because it comes out very nicely with all the attributes and everything. You can read it using this open dataset command. You just give it a file name and you'll get back this Xarray dataset that looks exactly like the one that we brought to it. You can check that these are identical to what I wrote, and they are. I knew I added a little bit on MATLAB. Okay, so the first one is usually it's common, at least in my work, to read a collection of many NetCDF files. This happens with model output, where you write a NetCDF file every month or something. There's a little documentation on how to do that kind of nicely. And for anything, well, there's a bunch of other formats that we support, but then for things like MATLAB files and HDF5 files, these are very common. You can't directly create an Xarray out of it. So usually what will happen is you have to use some other package like SciPy or H5Py to read that. And then you create a little data array from those, and then you assemble things. So if you find yourself having to do that, there's a little documentation on how to create a data array from scratch. We didn't do that here. We just read from disk and it all came out very nicely. But that's always, that escape hatch is always there. Let's see. Oh, we're at time. Paige. I have a little bit that's more of a demo still, so we could stop here or we could keep going. Up to you.
Maybe we'll stop here. There are a couple questions that have popped up.
Okay.
And we can let participants go through the rest on their own. Thank you so much. This has been great. So a couple questions, some of which have kind of been answered on Slack, but can Xarray deal with grid interpolation? Does it have some built-in scipy.interp.grid data like thing?
So grid data, if I remember correctly, is more from like a general points that are kind of not uniformly distributed to a uniform nice array. Answer is no. You would have to create that, I think, on your own using grid data and then wrap it up as a nice Xarray thing.
Okay, it was suggested to try using XESMF for regridding that is built on top of Xarray.
Yeah, that's also a good one. For simple interpolations, you could do ts.add.interp, and you can do something like this would be a uniformly ranged. Oh, that might take a lot of time. Oh, yeah, it was done. See, so you could do something like that. So very simple stuff, but for more complicated things, you have to look somewhere else.
Okay, great. Another question got answered. And here's a question again for MATLAB users. Is there a tutorial or documentation on building out all of the Xarray metadata, given that many people here are MATLAB users trying to make the switch?
No tutorial. I've thought about writing it, but I never got around to it. The challenge is always every MATLAB file is different because the person that writes it uses their own little convention for saving stuff. So I found that there's a lot of just looking at what each variable is and then doing some detective work to figure out which one's the right dimension and then creating it. So it's a little painful. But yeah, there's no easy answer just because there's no standard MATLAB file convention.
Okay, yep. Thanks. We have a question here on, can one use CF metadata in Xarray, where CF is climate and forecast?
Felipe, he's setting me up. So what he's referring to, so we are very lucky in Earth Sciences. We have a very standard data format, netcdf. And then on top of that, we have very standard attribute conventions. This actually ties into the previous answer on MATLAB. So things like standard underscore name are a standard attribute. Similarly, units and axis, long name too, but standard name is kind of like a very standard terminology for various common variables. So like longitude, the standard name for that is longitude, even though the actual name in this data set is lon, the standard name is longitude. And so what Felipe is trying to get to is there's this little package. It's called CF-Xarray, which lets you use, so that's, we've been talking about just using metadata that's in the data set. This is one level higher. This lets you use the CF metadata, which is kind of special and standardized to do cool things. So here, for example, remember the ts.air has a dimension lat. This is kind of annoying. Some other data set might come along and it has dimension latitude, and then you'll constantly have to keep changing the name. Or you could use the CF-Xarray thing, and it's smart enough to say, hey, latitude, that's a standard name. For this data set, that means lat, so I'm going to translate it. So this is like taking that metadata idea and then moving it further along. And you can end up doing lots of cool things there. So yeah.
All right. I think that covers all of the questions that I see in Slack.
Okay. So I'll add one little bit, which is this next section that we didn't end up doing is all about how Xarray ties into other Python things. So definitely scroll through. Again, it's mostly meant as a demo, and you can see kind of cool stuff. And the real thing I want to point out is this little bit. There's a bunch of other material that you can get to after this. This is super basic, very conceptual. You can go to the tutorial, which we've been working on now. It has a bunch of stuff. You can see on the left, there's fundamentals, which is basically a 4-hour tutorial that we do at SciPy. There's more intermediate stuff and more complicated things. So if you want more, that's where you should go. And then there's a whole bunch of other stuff that could be useful as you work with Xarray. So yeah, thanks for listening.
Perfect. Thank you very much, Deepak.
Yeah, thanks for inviting me.
It was a great way to kick off our Ocean Hack Week.